This is number 85. So they give us the Ka value for a weak acid. So let's start by writing out the equation. HNO2 plus water makes a hydronium ion plus a nitrite ion, and it's reversible. And so it tells us using the Ka value, find delta G standard. So we have to look up the K value in our list of Kas for weak acid, which is 4.5 times 10 to the negative fourth. And so the relationship between delta G and K is delta G standard equals negative RT times natural log K. So we can easily find delta G given the K. So delta G standard would be negative 8.31 divided by 1,000 kilojoules per mole times Kelvin times temperature is 298 Kelvin times the natural log of 4.5 times 10 to the negative fourth. And so our delta G standard is equal to 19.1 kilojoules. Okay, and then it's asking us for what delta G would be if it was at equilibrium. So solving for delta G standard just makes a relationship between K and this delta G. So we notice that delta G is positive under standard conditions, and again that's meaning that if we had this as 1 molar, this is 1 molar, and this is 1 molar. So we know in order for delta G standard to be 0, the K would have to equal 1. Because the Ka is 4.5 times 10 to the negative fourth, that's less than 1, which shows us a more reverse reactant favored equilibrium, meaning that the reverse direction is more favorable, so it's more spontaneous, and the forward direction would give us a delta G that's positive. Okay, if we are at equilibrium, then delta G, notice not standard conditions, is 0, meaning that we're not going to have 1 molar of the reactants and products at equilibrium. And then the last thing asks us what the delta G would be if we have these concentrations. So if we have these concentrations and we know delta G standard, we're going to do delta G standard equals delta G plus RT times natural log Q. So now we know the delta G standard is 19.1. We don't know what the delta G is under these conditions, plus 8.31 over 1,000 kilojoules per mole times Kelvin, times our temperature is 298 Kelvin, and we're going to do natural log Q. So this is where we're going to put products over reactants. So they give us that the H concentration is 5 times 10 to the negative second. So over here we're doing 5 times 10 to the negative second for the H concentration. The NO2 concentration is 6 times 10 to the negative fourth. And then our reactant is 0.2 molar. And so we simplify for this. We do natural log of that times 298 times 8.3. And we subtract all that from 19.1, and so we're going to get a delta G for this as negative 2.7 kilojoules. And so looking at that, under these conditions the forward reaction is spontaneous. It's not at equilibrium. It needs to go more forward to reach equilibrium. That's it.